Right, folks, it's great to be here. Today, I want to present work from my group on the work we're doing on robot perception, and I would like to touch on three main aspects: hierarchical representations, certifiable algorithms, and self-supervised learning. Typically, I cover these topics in a much longer presentation, 1 hour presentation. So in this case, I will keep it short, and I will keep it a little bit high level. With my group, over the last few years, we've been pushing, we've been pushing the state of the art in robot perception and SLAM in three main directions that I'm summarizing in this plot. Some of these directions are pretty intuitive. For example, robustness. We like algorithms which are more robust to noise, outliers, and domain shift. We would like algorithms which are more scalable in terms of the scene size and supervision. But at the same time, if you look at the vertical axis, we are also trying to push for algorithms which enable a higher level of autonomy and scene understanding. So just to make sure we're on the same page about this, you can think about the state. Example of scene understanding. If you are very low in terms of scene understanding, maybe you just understand the geometry, and you can tell the robot to go to position X, Y, and Z. We are pushing for robots that have a little bit of a higher level understanding and can execute complex instructions, such as go grab me a cup of coffee on the desk. So just to make sure we're on the same page about these three axes, let's populate maybe in a qualitative manner a bunch of data points in this plot. You can think about the state of the art in SLAM being roughly the one I'm showing in the plot. We have developed a lot of robustness. Algorithms are pretty much plug and play. They're fairly robust, and they scale to fairly large environments. For example, the map I'm showing here is some multi-robot SLAM dataset covering tens of kilometers of trajectories. At the same time, SLAM algorithms, the traditional instantiation of SLAM algorithms is mostly about geometric understanding. So we'll not have a lot of components on the vertical direction. They will not have much scene understanding. On the other hand, if you look at the state of the art in supervised deep learning and 2D semantic segmentation, here you start getting semantic information. So you get a much higher level of scene understanding, but these techniques are mostly bound to operate close to the trained domain. Therefore, both the robustness and the scalability is pretty limited. And of course, things go even worse if you're thinking about 3D deep learning instead of 2D. So what we want to push for, the goal of our research is really to develop scalable, robust, self-supervised algorithms for real-time scene understanding. In the rest of this presentation, I have three parts. I'm going to tell you about the progress we have made, again, at a high level along the three directions of this plot. And I'm going to start with the direction of scene understanding. So part one is about high-level and large-scale scene understanding. And I'm going to tell you about the transition we are seeing, which is going from SLAM to metric-semantic mapping and 3D scene graphs. So why do we need metric-semantic mapping? Well, of course, if I want to tell my robot, go grab me the cup of coffee on the desk, the robot will need to understand the geometry of the environment in order to avoid obstacles, but we'll also need to understand the semantics. We need to understand where is the cup of coffee, where is the desk. Therefore, we need metric-semantic maps. Starting in 2018, we started pushing on a real-time metric-semantic SLAM techniques. And at this point, many of you have seen Chimera. Chimera is a library for metric-semantic SLAM. Is taking standard camera and IMU data, is using 2D semantic segmentation, and then is back projecting the semantic segmentation into a 3D metric semantic mesh, which is the one that you see here in the video. But we are not the first, of course, to think about metric semantic SLAM. There is Andy here in the audience. This is largely inspired by semantic fusion, a mesh-based version of semantic fusion. And of course, there are many new proposals about metric semantic SLAM. The things that still stand out to me about Chimera is that there are three elements. First of all, we are doing this post-graph and mesh optimization, in which we're able to deform the entire mesh in response to loop closures in a very efficient way through a post-graph optimization problem. And also, we have a lot of robustness to correct loop closures through a tool which is called graduated non-convexity. And everything is running on CPU, which is pretty interesting considering that most of the other approaches are GPU-based. So going beyond Chimera, we quickly realized that metric semantic maps, this kind of meshes of flat metric semantic maps, are not enough for the type of scene understanding and for the type of autonomy we want from our robots. For instance, again, if I want to tell my robot, robot goes search for survivors near the fridge in the kitchen, a metric semantic map will not be very useful. The metric semantic map will not tell me where is the kitchen. It will not help the robot reasoning over relations between objects. For example, the fact that the survivors might be near the kitchen. In other words, in order to execute complex instructions, robots will need two extra things. The first one is that we'll need to understand semantics beyond objects. They will need to understand rooms, buildings, agents, and so on. Moreover, we need a representation which is able to reason over relations between elements in the scene. For example, the fact that the fridge is within the kitchen. So over the last few years, we have been pushing on novel map representations, and in particular, 3D scene graphs, which are metric semantic in nature. They also consider semantics beyond objects, for example, rooms, buildings, and so on, and they also capture relations between elements. So a 3D scene graph is the representation that you see here in the video. Essentially, at the bottom layer, you have a dense metric semantic mesh, but as you go up in the hierarchy, you're abstracting away the dense geometry into abstract semantic concepts, being objects, agents, rooms, buildings, and so on. Here, the layer of places and structures. Structures are essentially walls, ceiling, and so on. Places are a topological map representing traversability of the free space. So our contribution has been to push on this representation, really develop real-time algorithms that are able to build this representation from sensor data as the robot moves through the environment. So this effort led to Hydra, which is the name for our pipeline, for our system for real-time 3D scene graph construction. Hydra will start, essentially the robot will start without prior knowledge of the environment, and through Hydra will slowly reconstruct the 3D scene graph of the environment itself. For example, while moving, we'll populate a metric semantic mesh of the environment. At the same time, we'll estimate its own trajectory, which you see in purple here. We'll extract objects from the mesh. We'll also identify skeleton of traversability, like this graph of places out of the free space of the map, and we'll cluster the graph of places into rooms, buildings, and so on. So this is the first nice extension to SLAM. Now we are not only doing SLAM, we're also thinking about 2D semantics, which is projected back on the 3D mesh, but also to reason over rooms and buildings and so on, as well as places. We are starting to use other tools such as graph theory, topology theory, and so on. So through Hydra, we're able to get essentially a geometric clustering of the rooms, buildings, and so on. Of course, this is all open source, but would be also nice in many cases to identify which type of rooms the robot is moving in. For example, here we identify that there are 2 rooms, but we don't know if a room is a kitchen versus a bathroom. Therefore, we also pushed on new architectures for graph neural networks to classify nodes in the scene graph. And in particular, we developed the neural tree architecture, which is an architecture with probable performance guarantees that taking objects in a room will classify which type of room the robot is moving in. So the ultimate result is something like this. The robot is starting in a completely unknown environment. In this case, it's a kitchen. And as it explores, it's building the mesh representation of the environment, is estimating its own trajectory, is clustering different objects and identifying the semantics of these objects. You can see the sink, appliances, chair, table, and so on. And then this neural tree architecture is going to populate the semantics of the different rooms, for example, kitchen, hallway, and so on. In the latest paper about Hydra, we also proved a fairly fundamental, which I really like, which is this kind of 3D scene graph representation can be understood, of course, as graphs, where the nodes are spatial concepts and edges represent relations. But this kind of hierarchical representations have low tree width, which means the tree width is a measure of complexity of a graph. If you prove that the graph has low tree width, essentially you are proving that you can do efficient inference over the graph, which is a pretty cool fundamental result. So we're doing robotics. So the nice thing is that we designed Hydra to be lightweight enough and to balance the use of GPU and CPU in a way that can run in real time on a robot. So in this video, I'm showing Hydra running on a A1 quadruped. So you see the robot moving in the environment. You can see the 2D semantic segmentation, and the use of the scene graph being built in real time, as well as a top view of the scene graph, which is showing up over there. So the scene graph is making sense here. The scene graph is picking objects, is clustering different rooms in the environment, but probably the most important part of this slide is the runtime table that you see here. So the runtime is describing the time it takes to build a layer of objects, places, and rooms in Hydra using Xavier NX. Xavier NX is just a small credit card-sized computer, and you can see that we can build all the layers in a matter of milliseconds. Our work has been also pushing on extending these pipelines for metric-semantic understanding and 3D scene graphs to multi-robot systems. Here I'm summarizing just two main efforts in a single slide. On the left, you see Chimera Multi, which is an effort to extend Chimera to multi-robot systems. This is been something we've worked on for a long while. We have transactional robotics last year, but also we're still working on deploying these on real problems. And indeed, we have a new paper at Tyros 2023. The idea in Chimera Multi is to have multiple robots building metric-semantic meshes using Chimera, but also the fact that when the robots are meeting each other, they can find loop closures and compute a globally consistent trajectory through distributed optimization. So the approach is fully distributed. We'll get a metric semantic mesh of the environment and is also robust to outliers in the loop closure detection through a distributed version of rather than non-convexity. At Tyros this year, we also went a step further, thinking about multi-robot extensions of 3D scene graph construction. And we have Hydra Multi, which is the multi-robot extension of Hydra, in which multiple robots are building their own scene graph, and then they're communicating with the base station to jointly optimize the scene graphs in a single, globally consistent representation. With Hydra Multi, we're in early stages, I would say. The pipeline is still centralized, so we rely on a central computer. But there are cool things in which we exploit essentially the hierarchical structure of the scene graph. For example, we define hierarchical descriptors for loop closure detection, and we use these descriptors to match pieces of the trajectory across different robots. And again, we have robustness to outliers using rather than non-convexity. So I was motivating at a high level the need for metric semantic and 3D scene graph representations. The question is, are they actually useful in practice? And in this slide, I'm arguing that the community is realizing more and more that scene graphs are likely to be a good representation for a number of high-level tasks in robotics. So the three works at the top of this slide are showing that with scene graph, you can start doing more efficient path planning through the hierarchy of the scene graph. You can use the scene graph for reinforcement learning-based object search and get a boost in performance. And you can also use scene graph to reduce multi-robot communication. More interesting, so the top ones are work from my group. More interesting, the work at the bottom are works from other groups, also seeing that there is an advantage in using these representations. For example, there is a Coral work on task planning. It is called taskography using 3D scene graphs. And there are more recent work on both task planning as well as goal navigation, showing that scene graphs are a good representation for these tasks. There is much more. I believe there is much more to be done on task and motion planning, human-robot interaction, visual Q&A, monitoring prediction, and so on. So hopefully in part one, I convince you that we have to move from SLAM to metric semantic mapping, and 3D scene graphs are a good representation to think about the future of mapping. In part two, which I will keep in 3 slides, I'm going to talk about robustness instead. Okay, so this is a summary in 3 slides of maybe 6 years of work of my group. I'm going to talk about certifiable algorithms for robot perception. So what is the context here? The context is that in the previous part where we built scene graph, in the back ends of these nice videos that I'm showing, at the end of the day, we're solving just a bunch of estimation problems. For example, we are solving estimation problems in figuring out the pose of objects from sensor data, or we are solving estimation problems in reconstructing the trajectory of the robot as in SLAM. The nice thing is that despite the diversity of these perception problems, object estimation from point clouds, object estimation from images or SLAM, at the end of the day, these estimation problems can be thought of as an optimization problem. In this optimization problem, we're trying to estimate a variable X. For example, let's think about this as the pose estimate of the object you want to localize. And we are given measurements yi. which can be understood as maybe detection of key points in the image. And we want to compute the X by minimizing a residual error, which is measuring how well given estimate is explaining the measurements. And of course, we have a large set of measurements M. So in practice, the roadblock is that many of these measurements are largely incorrect. They are outliers. Okay, for example, if you want to do a pose estimation, object pose estimation, you want to approach a pose estimation problem, some of the key points we detect might be correct, might belong to the object. Some others might be outliers and might be completely wrong. Therefore, we have to figure out how to estimate X in a way that is robust to these outliers. Well, you might say people in robust estimation, 60 years ago, they already told us how to solve this problem. They told us we just have to add a robust loss function in front of our optimization problem. In my case, this is the RO function. What people in robust estimation didn't tell us is how to solve the corresponding optimization problem. And indeed, has been known for a while that for typical choices of RO, this problem is probably hard to solve. You cannot solve it in polynomial time. Just to trivialize the state of the art in robotics and computer vision, the typical approaches to solve this problem are either local solvers, think about gradient descent, which are essentially starting from an initial guess and going downhill. Well, in many cases, we do not have an initial guess, and also it is known that these approaches are easily stuck in local minima. The alternative in computer vision is RANSAC, which is a very elegant algorithm, but for those of you who are familiar with RANSAC, that will essentially apply to low-dimensional problems, will not apply to things like SLAM. And in both cases, these type of approaches will just fail without notice. They will give an estimate for the X. The estimate can be completely wrong, but they will not be able to tell you that the estimate is wrong. So over the last several years, we have been pushing on this idea of certifiable algorithms. The idea of certifiable algorithm is very simple. Certifiable algorithm is one that computes an estimate and either certifies that the estimate is the optimal one, is the best you can get, or otherwise is able to detect a failure. Okay? So again, we want to solve some optimization problem, which returns a robust estimate. Either we solve it and we provide guarantees that we solve it correctly, or we declare failure. We've been working on these topics for a number of years. The truth is that rather than having a single algorithm at this point, we have a toolbox of algorithms. And I can summarize the set of algorithms we developed in 3 classes. There are algorithms based on graph theory, which are pruning outliers, are just detecting and isolating outliers. There are algorithms based on graduated non-convexity, which are providing a heuristic to solve this optimization problem properly. And the last set, which is the one I'm most excited about, is the work on semi-dynamic moment relaxations, which can provide optimality guarantees on the result of this robust estimation problem. Of course, I will not have time to enter into the technical details here, but as output of this research line, essentially we have the first algorithms for robust estimation in robotics that can compute provably optimal estimates. So just to give a flavor of what is the practical impact of figuring out this robust estimation problem, I'm summarizing in this slide the type of results we get in 3 problems. Object pose estimation in point clouds, the problem over there. Object pose and shape estimation in the middle, and robust pose graph optimization. For estimation from point clouds, we developed teaser++, which is an algorithm for pose estimation robust to 95% random outliers. 95% means I give you 100 measurements, 95 of them are complete garbage. The algorithm is still able to figure out the 5 correct measurements, and it's running in real time. The other one is a little bit more. Not only is estimating the pose of the object, it is also looking at the shape of the object. Much harder problem, so the robustness goes down to 70 to 90%, but still great robustness to outliers. And finally, robust pose graph optimization, in which you have robustness to 70, 90% of outliers. And this algorithm is working pretty well. Indeed, MATLAB decided to include it in its navigation toolbox. And is also part of GTSAM. So if you are doing SLAM, if you have problems with outliers in the loop closure detection, try graduated non-convexity, and robust pose graph optimization is a pretty robust algorithm at this point. Okay, so for the last part, I have around 30 seconds. I want to tell you about going beyond human annotated data sets and thinking about self-supervised object perception. The truth is that I will not tell you about the technical contribution. I will tease you about what the contribution is about. So in the previous part of the talk, I argued that right now we have very effective algorithms that going from measurements, for example, key point detections, will figure out a robust estimate, for example, a robust estimate of the pose of the vehicle in this case. In practice, these detections are produced by neural network. There is a neural network which is figuring out semantic features of the car in this case, and this is what is called the perception front end. So the question that we have been asking in a bunch of recent papers, including a TRO paper and a recent RSS, is now that we have certifiable algorithms to solve the back-end estimation, can we use them to self-supervise the neural network at the front end? Instead of just manually annotating data and learning from training data, can we use the estimation algorithms to provide a supervisory signal to the neural network? And in the TRO paper and RSS 2023 paper, we have pretty compelling results showing that you can learn for object pose estimation, you can learn from real data without supervision. Again, no time to get into the technical details, but these two papers are the main ones describing this line of work. The thing I'm excited about is that, so far we've been thinking about maybe object detection. I've been describing how to go from images to features to robust estimates. The same idea applies to object detection in point cloud. The same idea applies to SLAM, right? There is a front end and there is a back end. Now that you have very good tools for the back end estimation, how do we self-supervise whatever is coming in the front end? So I think there is a lot of research to be done in this area. So I'm running out of time, so we'll conclude here, summarizing the three main takeaway points of my talk. Again, we'll be pushing the state of the art, trying to push the state of the art in these three directions: robustness, scalability, and high-level scene understanding. And our main conclusions is that the next generation robot perception requires metric-semantic hierarchical maps, and of course, real-time algorithms to estimate them. The second conclusion is that safety-critical application will require certifiable algorithms that are able to distinguish correct estimates from incorrect ones. And the last point is that once we have certifiable algorithms that are able to distinguish correct estimates from incorrect ones, we can use that information to enable self-supervised learning, and we can learn without supervision. That's the time I have. I will thank the sponsors, and I will thank you for your attention. I'll be happy to take questions.
Excuse me. So currently, I get the news from ICCV. So all the people should exactly cannot stand in the meeting room and should be able to sit, because if you violate this rule, and you have to be out. So I recommend you to just directly sit, because I just get this information. So people stand here, sit here. Could you please sit on our seats? I just for a couple of minutes. Okay. So
okay.
Yeah.
Thanks. Yeah, I think we had a couple of questions.
Yeah, it's a very hot topics, and yeah, thanks for cooperation. Yeah. Okay. Okay. So maybe we can start. Okay.
Can you still take the questions?
Yeah.
Okay. So you guys have questions? Go ahead.
Yeah.
So for the only language to
yeah, so there are two flavors here. There is the version without outliers, and there is the version with outliers. Without outliers, actually the semi-definite relaxation will have a very fast solution, which you might know about, which is SC-sync, which is as fast as GTSM. Like, so you get global optimality without extra computational effort. For the case with outliers, the problem is much harder, and unfortunately, we don't satisfy technical requirements for Buer and Montero, so it is not feasible. We do not have a very fast solver in that case. So for the SLAM part, like the moment relaxation, at this point is more of theoretical interest, because it's the first approach to certify global optimality. It's not something that you can run in real time on a robot. Great question.
The third question is, in terms of the species, have you ever seen about the large language model actually could be a sweet spot in the future, and how do we foresee in the next couple of years how this kind of going to shape?
Yeah, that's a great question. I was chatting about that a little bit more at the scene graph representation workshop yesterday. There is a huge role for language for scene graphs. And at one level, for example, if I had to redo this chimera from scratch, instead of doing the traditional semantic segmentation, I would use clip feature for the mesh representation to open set. So you have seen works like, concept fusion, for example. There are recent works which are doing the mesh reconstruction or the low-level metric-semantic map using language embeddings instead of just fixed semantic classes. I think that's a great idea. Fixed semantic classes will not be generalizable enough. And there is also another role for language, which is to enable zero-shot classification at the top layers of the scene graph. Maurice was mentioning something about that in his talk. But essentially, we also have words in which, given the objects in a room, we can use language to classify the type of room the robot is moving in without relying on training data. So yeah, language can be very, very useful. Yeah.